Good morning, everyone. I'm Jeremy Elder, manager of the sales team here at EMAG in Farmington Hills, Michigan. I want to thank you all and welcome you to our webinar on the VSC 400 power skiving machine. Our staff, sales, service, and engineering group are always available to assist you with any needs or concerns that you or members of your team may have, and we certainly appreciate your time. Now I will hand this over to our colleagues in Germany to begin the presentation. Thank you.
Hello, everybody. Also, a warmly welcome from my side. My name is Martin Abendschein. I'm the responsible application team manager, also here for the VSC 400 PS machine type. And together with me is Mr. Daniel Nille.
Hello, my name is Daniel Nille. I've been working in development at EMAG for a long time. And in the last few years, I'm responsible for the development of the power skiving process.
Okay, so let's start with our webinar. So first of all, I want to talk about the history of power skiving. So power skiving is not really an old application or old process. It was already developed beginning of the 20th century. But during this time or at this time, the machine concepts, the toolings were not that good that it was really established in the market. So in the past years, there was a very big development, especially for the tool, from the tooling side, but also from the control side. And also the machines are now able to handle the power skiving application itself in a very good manner, so that we can use this now beside of the shaping or gear hopping processes as a third application field in the market.
Yes, how does exactly power skiving work? If we have a coupling between the main spindle and the milling spindle, you can imagine it like a gearbox where the teeth mesh with each other. If we have a look at the tool is in the machine under axis crossing angle. And so if the teeth goes into the part and comes out, he makes a movement in Z direction. And so every teeth makes a small cut and cuts the gap. For this we need the Z-axis that we can machine the whole workpiece, the whole length of the workpiece. And our machine also has a B-axis that's important for setting up the B-axis, the axis crossing angle. Normally we work with 20 degrees axis crossing angle, but we are also able to machine with axis crossing angle between 5 and 45 degrees. We have had already a test with a special worm gear. Here you can see it. It has an angle 47.5 degrees. That's also here. There you can see it. That's also possible with our machine. Which axis do we need additionally? We need X-axis. The X-axis is for positioning of the tool in the middle of the workpiece. And we need the Y-axis for the infeed. Yes, if you have a cylindrical tool, you also need the X and the Y-axis for the cover angle. Here we see we have a video as a demonstration. We machined here a cylindrical gear with model 1 and 46 teeth. We had 2 rough cuts and 1 finish cut here. And we machined it with air to get the chips out of the process. It's very important to get the chips out of the process because otherwise they clamp between the workpiece and the tool, between workpiece and the tool, and you get a very low tool life then. The finish cut is not so fast than the rough cuts, that we get a good quality at the tooth trace. Yeah, what is the application for power skiving? We can produce internal and external gears with power skiving. If we have a look at internal gears, other possibilities to machine internal gears are the processes broaching and gear shaping. Broaching is not possible, for example, if we have a shoulder at the end of the gear, and with broaching it's not possible to produce flank modifications. Gear shaping is also possible for internal gears, but it's slower than power skiving. If you have a look at external gears, the processes that are possible are hobbing or gear shaping. Hobbing needs more outlet at the end of the gear because of the diameter from the tool. And gear shaping here is also slower than power skiving.
So before we go ahead, Daniel, there was one question. And this maybe we can address to Jeremy. The question is, in the video you have showed dry processing. Can it also be done wet? What are the advantages?
So yes, the short answer is yes, you can do power skiving with a wet process. The customer would obviously have to take into account fluid maintenance and upkeep. Advantages to that are cooling the tool in the cutting area. But also, as Daniel mentioned previously, we prefer to do that process dry, keep the chips out of the cut, not have any clinging or buildup inside of the workpiece where we could affect tool performance. So short answer is yes, but there are some considerations as far as coolant maintenance and upkeep and the type of fluid you use.
Yeah, and another application for power skiving is complete machining. It's possible in our machine to do the turning process and the power skiving in one clamping. That means you have the perfect concentricity between some references and the gearing. What are the advantages of power skiving? We have, for example, we have lower cycle times than with shaping, and it's possible to produce gear modifications, for example, end reliefs or then we can achieve high quality and low surface roughness.
Okay, so now we are coming to the process chain itself. Here on these slides you can see the current process or the traditional process, and on the lower line you see the process with power skiving. So for the traditional process, of course, we do have always two operations for turning, op 10, op 20. Then we have the shaping, we have the deburring, we have the hardening at the end. We have also the grinding operation. By the way, the blue marked processes can be done on EMAG machines. So here we do have 6 operations, 6 processes. If we now compare this with the process chain including power skiving, you can see we have only 4 processes, 4 operations. So first of all, again, with the turning operation op 10, but then by use of the VSC 400 PS machine, we can combine the turning of the second side, the power skiving, and even the deburring of the parts afterwards in one machine. And then we have the hardening, and after that we do have the grinding.
We actually got another question. What are the advantages of combining turning and power skiving? Why are the processes not performed in separate machines?
Oh, that's a very interesting question. And I think also Jeremy can give us the answer.
Sure, I'd be happy to. So obviously, when you have 2 separate machines or 2 separate processes with the component, you hard turn and then you move it to another machine, you have considerations to think about regarding clamping, tolerances, things of that nature. So having the ability to pick the component up in a single clamping, take your hard turning cut, and then follow immediately in the same clamping with your power skiving is going to give you a great advantage as far as repeatability and also tolerance capabilities.
Okay, thanks, Jeremy. And beside of the answers from Jeremy, I also want to add some more points which are very relevant, very important for that. Beside of the accuracies which are higher if you can do the turning and the power skiving process in one machine, in one clamping already. So we also have a very unshortened throughput or full running time of the complete process from the raw part to the finished part, because we have less process steps inside. We need less machines. This means we need less footprint and of course also less power consumption. So we can save also here a lot of costs from this side. And at the end, of course, we have also a lower investment. We have lower capital commitments because we have less machines, and altogether makes the cost per piece cheaper than compared with the normal traditional way with 6 process steps. If we have now a look how you can use this machine, we have 2 possibilities. The first possibility is to have it as a standalone machine, like you can see it here on the left-hand side of the presentation. So here we do have the machine itself. Then we have our L-type conveyor band, which goes through the machine. In this case, the operator puts the raw part on the pallet. The pallet will be transported into the pickup area. Then our machine picks the part by itself by use of the clamping chuck, transports the part into the working area. Then we are doing the turning, the power skiving and the bowing process, and puts the finished part back on the conveyor. The finished part comes out here, and the operator can here take the finished part out and put another raw part on. This is a standalone solution, so you can put this machine wherever in your production hall where you need it, completely independent. If we are talking about a complete production line principle, then of course we can also use the same machine type, the VSC from the PS, but now we change to a so-called shuttle automation system. And here we do have 2 pallets on the shuttle, one for the raw part, one for the finished part. The principle is the same. The raw part will be put on this shuttle, on this pallet, by use of a gantry or a robot system or anything else, then transported into the machine. We machine the part, the finished part comes out, and the robot or gantry system can take the finished part here and put it to the next process in the process chain.
What options do we need for power skiving? We need a main spindle and a milling spindle with a direct drive. And here we have high resolution encoder. That's very important that you get a good synchronization between the 2 axes. Also, we have a very rigid B-axis. You can see it here. It's mounted on both sides on the machine. It's a very rigid B-axis. If we have a look at the B-axis now, we also see we have here 2 tools, 2 milling spindles in front, and in back of the milling spindles we have 6 turning tools. Yeah, some technical data from the machine. The maximum workpiece diameter is normally 340 millimeters, but it depends on the clamping. If you have the possibility to clamp the part in the inner side, it's also possible to produce part with 400 millimeters diameter, 400 millimeter diameters. The maximum workpiece height is 160 millimeter, but it also depends on the clamping device. The clamping device can have a maximum swing diameter 420 millimeters. I already told you we have 6 turning tools on our B-axis. They are mounted with a BMT65 interface. Here we have possibility to put in 2 power skiving spindles in our B-axis. 1 spindle is also possible, but if you use 2 power skiving spindles, we have some options more. One option is that you can produce 2 different gears, and if you have also possibility to use 2 tools on 1 spindle. It depends on the part, because sometimes you have some interference contours then, but if it's possible, then you are able to produce 4 different gearings on one workpiece. The maximum speed of our milling spindle is 7,000 rounds per minute, and from our main spindle 3,400 rounds per minute.
Sorry to interrupt you, Daniel. There is another question coming in. I think Jeremy can answer this question as well. So the question is, can power skiving be done with hardened material 60 HRC?
So yes, you can power skive hardened material. The concern with that, of course, comes down to tool life, which is a common occurrence or common issue in the industry right now. So many of the tooling suppliers are working on new and improved cutting tools to help with that tool life, but it would be a concern and a consideration the tool life that you would have or tool performance when power skiving hard materials.
Okay, thanks, Jeremy. And there's already another question. Daniel, I think this question is for you because it's according to the process. So, what accuracy do you achieve by coupling the milling and work spindles? Where are the limits? How is the process programmed?
Yeah, it's not so easy to say. The accuracy of the coupling depends on the speed from the spindles, because you get a lot of signals and the control has to handle these signals. That means if you're running faster than sometimes the control is too slow then. But we tested it. We are sure we are able to do power skiving with the maximum speeds of our main and milling spindle. This means 7,000 rounds per minute from the milling spindle and 3,400 from the main spindle. And maybe I want to tell you something additional about the hard power skiving. Our machine has the possibility to do hard power skiving. Our software is able to do it, and we also have a probe that we can detect the gearing, and then we fit perfectly with the tool into the already existing gearing. That's possible. Yeah, which gears can we produce with power skiving? We can power skive straight and helical gears, spline and running gears, maximum diameter approximately 350 millimeters inner diameter and outer diameter 400 millimeters. And we can produce up to 4 different gearings per workpiece. That's possible. We already had tests up to model 4. This is possible, but I'm sure it's possible to produce to power skive our also bigger models, because the machine is very rigid and there should be no problems. And we can do the turning and the power skiving process in one clamping, that we get the perfect concentricity between the references and the gearings.
Okay, Jeremy, now comes your part for the machine main components.
Sure. So a little bit about the VSC 400 PS, guys. So this is a long-standing platform for EMAG. The VSC series has been around for many, 30 plus years. It's a good, solid platform. Includes, of course, our monolithic polymer concrete base, the very rigid hydrostatic guiding principle, a good symmetrical design where the spindle is directly over your cutting area, and complete with the typical EMAG cooling solutions where we control thermal expansion and temperature by cooling the spindles and the turrets. And as we talk about that a little more, I think Martin will jump into each specific detail on the machine and some of the advantages of that.
Thanks, Jeremy, for that. Okay,
Sure.
so let's start with the machine base. As you can see here, we have a typical U-shaped base made in mineralite. So why mineralite and not gray cast iron? It's quite easy, because mineralite has an 8 times better damping weight than gray cast iron. And this is especially for milling processes like we do have in the power skiving process a very big advantage, because the vibrations which we have in the milling process has to be damped down as fast as possible to avoid bigger tool wear, to avoid worse quality of the surfaces in the gears and so on. And here you can see the amplitude. This is the damping amplitude of mineralite against gray cast iron. So this means we can damp down the vibrations much faster, and this will help us to have better surface quality and longer lifetime of the tools. The second point, which also helps us in regarding the tool lifetime, is our hydrostatic guiding principle in the Z-axis. So we have a guide cylinder which runs in an oil film inside of a hardened liner to avoid any bigger pressures in case of a collision, and also to increase here the stability of the complete machine. Next point, we have a symmetrical design of the complete machine. So we have the U-shape in the machine base. We have the cross slide with the z-axis and with the x-axis, and the cutting force point is always quite similar in the symmetry of the complete machine, which allows us that the cutting forces will be taken over in the complete machine base in the best symmetrical way. Also for thermal stability, this is the best concept, because in case of changes according to the temperature increase, it will be always in a symmetrical way. And another point which I want to show you again here, we have here our hanging spindle. This means the workpiece is hanging vertically. So if we are now thinking about a machining of an inner wing here by power skiving, with a vertical principle, we go in with the tool and the chips can easily fall down due to the gravity and due to the vertical clamping situation here. So we make sure that the tools fall down. We don't have tool clamps inside, which will, in the worst case, damage the tool. And of course, will influence also the surface quality and the quality of the complete part. And the second point is the chips have the heat inside. So when the chips can fall down directly to the chip conveyor, we can transport the heat completely out of the machine, out of the process. If we are now thinking about an horizontal clamping, and we go in with a power skiving tool for inner rear gear machining, we have always the problem that the chips are still remaining inside the workpiece. So we have to take sure that we can blow them out, that we can splash them out or whatever, to make sure that there are no chips are inside. And this process is not that stable that we have it here with our vertical hanging spindle. And last but not least, as Jeremy already mentioned, we have our own coolant system. We have two circuits, one for the main components in the machine base, which means for the turrets, for the machine base itself, for the main spindles, and another one just for the e-cabinet. And here we have also a specialty. We do not cool down the complete system to 22 degrees Celsius, like others are doing that. We are just checking the ambient temperature outside, for example, 36 degrees, 34 degrees, and then we cool down the system to a gap of 2 degrees, which means the machine itself has then a temperature roundabout of 32 degrees, 34 degrees. And why we are doing this? Because if we have a shop floor without air conditions and we cool down the machine to 22 degrees, but the war part outside has no air condition and has a temperature of 36 degrees and comes into the machine, then you have already a difference in the temperatures of the war part and the machine and the process itself. And this will influence also your accuracy of the part. Therefore, we're just going with our coolant system around about ±2 degrees Celsius to the ambient temperatures of the production hall.
We got another question. Based on a maximum speed of 3,400 rounds per minute, do you recommend use HSS or carbide cutters in order to improve tool life? 3,400 rounds per minute is fast enough to handle carbide cutters. Yes, it depends on the diameter of the workpiece. If your workpiece is very small, then maybe it's not enough. But normally the gears that we machine on our machine, 3,400 rounds per minute, are enough. And which tools do I recommend? The tool life of carbide cutters is higher, but which HSS tools you have normally a shorter cycle time, because the cutting it's not when you in a turning process. Normally you can work with higher cutting speeds when you use carbide cutters, but that's not really possible at a power skiving process. That means carbide cutters have a longer tool life. HSS tools normally have a shorter cycle time. Yeah.
Okay, so now we are coming to the menus.
Yeah, that's a very important point. We come to the programming of the power skiving process. Your machine can be the best machine, it can be perfect, but when we're not able to do the programming, you won't get a good quality. especially if you use, for example, cylindrical cutters. These cutters have no clearance angle. Because of this, you have to move the tools out of the middle from the workpiece. And so you have a movement of all the axes. That means you have to move the X, the Y axis, the positioning of the workpiece and the tool, and everything at the same time that you fit into the gearings with the tool. And this is very complicated to do the programming. And so we decided that we will develop a user interface for power skiving process, which makes it possible for everybody to create a program without knowing, or even if he has never seen a gear before. You only have to enter the values that you get from the drawing, from the workpiece, or from the tool, and you enter it in the surface, and our surface creates the program and makes everything for itself. The surface makes calculation in the background, and that you're not able to make failures anymore. For example, if we have a look at this is the interface, the page from the tool. Here you can see some data that you have to fill in. On the right side, you see a picture of the tool. This is an interactive picture. Even if you always see highlighted in red which value are filling in at the moment, and the picture changes. For example, if you have a right-handed tool, the picture is a right-handed tool. If a left-handed, left-handed, and you can compare the reality directly with the picture, and so it's better for you won't make so much failures. Yes, then the other part is here, the interface for the workpiece or for the gearing. If we have a look at this, there are standard things that you have to fill in. They are all on the workpiece drawing, and we have here two special functions. It's single flank machining. With this, you have then two finish cuts. Then you can machine every flank separately. This makes normally a better quality, and you can, for example, choose that you have a helix angle on the left side 55 degrees and on the right side 54 degrees or something like that. That's everything possible. We can also produce bevel serrations, and we have one point that's rotation, serration location. That means that we can produce orientated gearing on the workpiece, for example, to a drilling or to something else. Here, as I told you, we have the possibility to make modifications. And for example, here we can program a grouting or end reliefs. And in this case, we have single flank machining. That means you can separately, you can do a different grouting on the left and on the right flank, side of the teeth. Here you can choose the corrections. You only can choose the correction which you want to see later in the EMAG feature correction page. That's good because you can do the corrections from the standard turning tools and from the power skiving tools then later in one page. And we calculate everything in the background that, for example, if you do a correction for the toolbar measurement, that is, yeah, you have to calculate it, because if you want to do a correction for 0.2 millimeters, then you have to do a different movement from the X and from the Y axis. This is the heart of our user interface. It's for the technical data, for the cutting data. You can add here cuts, you can delete cuts, you can copy cuts, and you can you can enter here every value individual per cut. For example, if we have a look at the axis crossing angle, we have here different axis crossing angle on every cut. And if we have a look at the tool, the position of the tool moves then. That means we have not always the same direct position of the x-axis, and we calculate in the background the optimal position that you always fit into the gearing. The same at the cover angle, we always calculate everything in the background. You don't have to calculate something external in a computer or something like that. We calculate everything in the machine in the background. One point which is important is the axis rotation, the Z-axis rotation. This allows you to cut only on one flank. One flank cuts better than the other flank, and so you can say, I use only one flank for every cut. This makes a better tool life. And also for if you have two finish cuts, then you can here set up, enter the rotation of the Z-axis that you only cut on a single flank then. Yeah, now we have some examples for gear quality, which we have produced in the last test. This was a gearbox with model 0.6 millimeters. And here you see in the profile, we had a deviation between 1 and 3 micrometers. This is then corresponds to quality 4. And then in the helix deviation, it's also a deviation between 1 and 3 microns, which corresponds to quality 3. And this is the pitch deviation. It's quality between 1 and 4. Yes, that's possible to do with power skiving.
Okay, so now we are at the end. Jeremy, do you have some words for the audience?
I just want to thank everyone for attending. We're happy to help with any questions that if we didn't get to live, we'll of course try to answer those via email or call after the presentation's over. Our group in Saarlach, Germany, where Martin and Daniel are happy to help with any questions, as well as anybody from our team here in Farmington Hills. So we certainly appreciate the time. We're very excited about this machine, and with the new electronic drive components and more of the gear processing we're seeing, I think the power skiving opportunities are in the market, and we're very proud to offer this machine as an opportunity to work with our potential customers and partners. So thank you.
Okay, so Jeremy, there came up already another question.
Okay.
Do you have experience in hard fine machining with power skiving?
Yeah, maybe I say something. Yes, we
I
have.
I'll let Daniel handle that one.
Yeah. I think we have experience in hard power skiving. As I already told, our machine has the possibility to do hard power skiving, but the problem at the moment is the tool life.
Yeah. Another question. Can profile modifications such as tip chamfer or tip relief be done with the power skiving process? I think you answered this already before.
Yes, it's possible. Of course, it's possible, but the machine has nothing to do because you grind this into the tool.
Yeah.
The profile from the tool is the tip chamfer and so on. They are grinded in the tool, and the process is the same. Yes, it's possible.
Okay, another one. Oh, I think, Jeremy, this is one for you. Is it possible to make spiral, barrel, and plate gears?
So it could be possible when you're looking at a spiral bevel type gear. We would have to actually look into that because you do a work area investigation, a tooling investigation, and look into our Z-axis travel capabilities because of how we have to locate our spindle in comparison to make that spiral bevel gear. So I want to say that yes, it's something we would definitely look at, but it would take some investigation.
Oh, okay. One more. So based on the comment about independent flank correction, can we enter individual corrections for the FHB lead angle error?
Yes, that's possible. I think I go back in the presentation. There you see you can enter here different helix angles, and then it's also possible to do separate corrections for both lead angles. Yeah. that's possible. No problem.
Okay. And now a common question. What is a good quality? Which tolerance classes can be achieved? Will you be showing the VSC 400 PS at the EMO? So the last question I can answer easily. Yes, indeed, we will show this machine on the EMA exhibition in Hanover in September. And for the other two questions, I guess, Daniel, that's up to you.
What is the good quality? Okay, what is the good quality? It depends on the workpiece. If you have a running gear, then you need a better quality. I think good quality is quality 6. Normally it's enough, but yeah, it depends on the gearing. Which tolerance classes can be achieved? I think normally tolerance class 7 DIN ISO is always possible, and in some cases, as we have seen, also quality 4 is possible.
Okay, another question. Can hardened gears also be machined with power skiving? Or I think this we answered already in the second one. What is the impact on tooling costs? Jeremy, what do you think?
Yeah, we talked about that a little earlier. So you can, the short answer is yes, you can power skive hardened gears. Your costs will be higher, of course, than if you're in the soft state, and your tooling costs will be higher. So that's something that has to be looked at. And like I mentioned earlier, there are conversations. Many tooling suppliers are looking for new and improved substrates and coatings and things of that nature to try to improve that tool life. So.
Okay. Another question. How are new tools changed into the machine? How does the tool change work? Tool setting and then quality control? Daniel?
Yeah, tool change is made by hand in our machine. You unclamp the tool, you put in the new tool, and you clamp the tool, the new one. It's very easy. Tool setting and then tool quality. Yeah, we have the possibility to do a 2-ball measurement in the machine. This allows us to make one cut which goes not to the end diameter, and then we can get the 2-ball measurement, the values of 2-ball measurement back to the machine, and do the finish cut after that. Then we get the perfect 2-ball diameter after at the first piece, first work piece.
And maybe here again, one more point regarding the tool change. As we mentioned before, we do have up to 6 turning tools on the turret beside of the 2 milling spindles. This means we do have another concept than some other companies in the market. So we have the tools on the turret already installed, so you can use these tools for the turning operation. You don't have to change the turning tool with the power skiving tool. So we have the turning tool holders for turning operations, and we do have up to 2 milling spindles for the power skiving and the bowing operations. So there is no automatic change necessary for that.
Yes.
Okay, another questions. The burr tool is insert or disc tool. Can we programming the burr tool, the burr workpiece only on the valves or finish pass? So the burr tool, insert or disc tool, it depends on the process. So in the process, we can do the burring by use of a turning tool and just turning the shoulder, the back shoulder and the front shoulder, and then have an air cut to remove the burrs inside the profile. We can, of course, then program the burr tool if we are using a turning tool. And here we can use HSS, but normally we are using carbide inserts for that as a normal turning tool. And the burr workpiece only on the valves or finish pass. Normally we are only deburring after the finish pass, because it makes no sense to deburr the part already after the valve power skiving process.
Yeah.
Okay. Is temperature compensation required during the process, Daniel?
No, normally not. If you use air, then it's absolutely no problem, because the air always has the same temperature when it comes into the machine. Sometimes if you use a cooling lubricant, then it can be better if you use temperature compensation, but it depends on the stability of the temperature from the cooling lubricant. But normally we don't need it.
Okay. Another question, no, they don't end. How serious stable is the power skiving process? Do you offer measurement, data feedback, and automatic process compensation? You or me?
Du.
Okay, me. Okay, so how serious stable is the power skiving process? So we can say our VSC 400 PS machine concept is one of the richest machine concepts in the market. So this assures that during the process, the machine runs always within the same parameters. We do have a coolant system inside the machine. We have the possibility to measure the parts by use of this two-ball measuring system and make a compensation directly back to the tool. We measure, we offer this measuring data feedback inside with the two-ball dimensions measuring system, or what would be the more precise method would be to use an external measurement machine behind the power skiving machine, and then measure the part there, and then have a compensation with these measured dimensions back to our tool management, which is also possible, of course. So, of course, we can do that. Okay, so I think we are coming now to the end. Thank you very much for your attention of our webinar today. And please feel free to send us upcoming questions which you have now or later, or which we did not answer during the webinar now, to our email address, communications@emag.com. And Daniel and myself are very glad that you joined us today, and we wish you a good day. Thank you very much.
Thank you.